Okay, so in order for us to do this, you want to rewrite this as an x squared plus 9 to the 1/2. So it is first times the derivative of the second. See how we used a um, uh, chain power rule? The 1/2 dropped in front, power went down by 1, stuff stays there, times the derivative of the stuff. And then plus the second times the derivative of the first. So I just did that derivative using the product rule and the chain rule, got my derivative, and then I just plugged in 4. Okay, now watch when you plug in 4. You get 11, and the half just comes down. This is 16 plus 9 is 25. When you square root that, you get 5. When you flip it, you get 1/5. And then 2 times 4 is 8. And then again, that's the square root of 25 or 5 plus times 2 is 10. This becomes 44 over 5. That's 50 over 5 for a total of 94 over 5. Okay. So you do have to know how to do the product chain, recognize when you have to use it. None of those rules are going anywhere. We're going to continue to use them in our applications of derivatives in the next chapter. Okay, so make sure that you realize that you have to know all of those rules as we go through this process. Okay, so that is just a little bit about chain rule, product rule kind of products, stuff like that. Okay, so today's notes are about some real life applications for the implicit differentiation process. So related rates are complicated, but they're doable if you always kind of follow along with the steps that I've laid out. It does make it a little nicer, okay? So we are always going to do for these problems 5 steps. And it's a silly, but I'm just going to call it dreads, okay? So our 5 steps, dreads. You have to draw the picture. You have to find what the rates and variables are going to be. What is an equation that relates those things? Then you're going to differentiate. Then you're going to solve. So to do these problems, we have to do 5 things. We're going to draw the picture. We're going to do the rates and the variables. We are going to find an equation that fits. We're going to differentiate. Usually we have to use implicit differentiation, some y prime sort of thing, or something of that sort. And then we're going to solve. We are going to use some of that Leibniz notation, but I'll walk you through that process when we get the chance. So I call these the dreads problems. These problems, again, follow these 5 steps and it will lead you to where you want to go. Once you set it up, the actual algebra of things, I don't think you'll find exceptionally difficult, but it's getting the information from the problem, like any word problem, and pulling that out, okay? So let's look at our first example here. It says air is being pumped into a spherical balloon. Don't go any further until you have drawn a sphere. Okay, so we've drawn this sphere. And it is, air is being pumped into a spherical balloon so that the volume increases at a rate of 100 cubic centimeters per second. So I know the change in volume per unit of time is 100 cubic centimeters per second. So I'm going to call that dV/dt. I'm going to show both those things because it's very important to realize that we are going to have to differentiate these things with respect to time, okay? So now I've pulled that part out. And then says, how fast is the radius of the balloon? We're going to stop. How fast is the radius? So we need to know dr/dt. So that would be centimeters per second. Increasing, when the diameter is 50 centimeters. Now, they mentioned radius. So in our sphere, let's put a little r, okay? And then if our diameter is 50, our radius is 25. Okay? Now let's go back for a moment to the dreads, the 5 steps. As I read the problem, I was pulling things out. I drew a picture. I wrote down some rates. I kind of have some variables in there, V for volume, R for radius. But now we need an equation that relates those things, okay? So the volume of a sphere is 4/3 pi r cubed. That relates my volume and my radius. So I have technically, as I've done this first few steps of the things, I've done step 1, 2, and 3. Okay, nothing crazy. I've just done those 3 steps. They kind of come along as you interpret what the problem is telling us. Now, the 4th step is to differentiate. We are differentiating with respect to time. I don't see a time in the problem. That's why we have to tack on a dv/dt, dr/dt. That's like v prime and r prime. And you're welcome to call them v prime and r prime, but I'm not going to, okay? So if I differentiate this with respect to time, since v is not time, since r is not time, I have to tack on a prime. So I'm going to, the derivative of v is usually 1, but this is 1 dv/dt. Now, this is just a constant in front of a variable. It's a power rule. So I take 4/3 pi times 3r squared dr/dt. That's our r prime. Now, I would like to clean this up a little bit once I have actually, got ready for, so that it looks a little nicer. I know v dt, the 4/3 and the 3 cancel out the 3's, so it's just 4 pi r squared dr/dt. Now I'm looking for dr/dt. So I should have enough information to substitute numbers for the other things. dv/dt I know was 100. R I know at the exact moment I'm looking for is 25. So you'll notice the dr/dt I can solve for now, and that will give us the answer that I want. So dr/dt is 100 divided by 4 pi times 25 squared. Now 4 goes into 100 25 times. So I can cancel out one of the 4, or the 4, and one of the 25s. So that is 1/25 pi centimeters per second. So what did this tell us? At the exact moment that my balloon is being filled with air at a rate of 100 cubic centimeters per second, when the radius is 25 centimeters, that means that my change in the rate, my instantaneous rate of change of my radius, it is increasing at 1/25 pi centimeters per second. The positives and the negatives are important here. If it's positive, the thing should be increasing. If it's negative, the thing should be decreasing. So the fact we got a positive answer for both is helpful because it tells us that we were on the right track. Okay? So that's your first introduction to a dreads problem. There are a lot. Okay? Let's do another one. So a common thread here, a lot of these problems have to do with geometric shapes and then the formulas that go with them. So volumes of spheres, volumes of pyramids, volumes of cones, volumes of a box, things you should know or can look up and then hopefully memorize. But don't overthink them. You guys are great at that. Okay, so remember, our first thing we're going to do is we're going to draw a picture. Now let's read the problem and let's look at what we've got here. It says a ladder that is 10 feet long is up against a vertical wall. The bottom of the ladder is sliding outward at a rate of 1 foot per second. Okay, so you'll notice that I have made a drawing: wall, ground, ladder. Okay, the ladder is a constant 10, so we don't need a variable there. The ladder is not changing shape. We're not smushing in the ladder. We're not changing the ladder, so just put a 10 there. But the top of the ladder will go down as it slides out, and so that is going that way. So we do have a rate sort of problem. Okay, so I put an X down here because it's going in the X direction. I put a Y here because it's going in the Y direction. You can call them height for H, G for ground. The variables are inconsequential. It's just how you set them up. So you decide what the variables are. It doesn't matter. Okay. It says if the bottom of the ladder is sliding away from the wall at a rate of 1 foot per second. So I know I called it X, so I have to say dx dt is 1 foot per second. Now remember, this was 10 feet, so all of our units are matching up. That's the rate. Anything it says per second is going to be in the rate category. Okay. So then it says how fast is the top of the ladder sliding down the wall. So we're looking for dy dt. How is that y changing at that particular moment? It says when the bottom of the ladder is 6 feet. I called that X. That is what they are referring to, when that bottom of the ladder is 6 feet from the wall. So let's look at what we've done. We have pulled out the ladder's height. We've drawn our picture. We've found our rates, the one they gave us, the one we're looking for. We know the exact moment when that's happening. Just like before, we knew the radius was 25 when we were looking at it. Here, we know that distance from the wall is 6 feet. So now we need an equation. Well, what is an equation that relates X and Y and 10? What is an equation that we would use that relates those three things? What's its shape? What kind of triangle? A right triangle. What's an equation that relates the sides of a right triangle? Huh? What is an equation that relates the sides of a right triangle? The Pythagorean theorem. So we know that x squared plus y squared has to equal 10 squared. Don't overthink these ones. They love Pythagorean theorem in these problems. They use them again and again. So don't overthink it. Okay. Now, every time we take a derivative of an x, we have to tack on an x prime, dx dt. Every time we take a derivative of y, we have to tack on a y prime, dy dt. Because we're differentiating with respect to time. Okay. So now it's time to differentiate. Okay. So this will be 2x. Tack on a dx dt. This will be 2y. Tack on a dy dt. The derivative of a constant is 0, so we don't have to tack on anything. Now we're ready to solve. Well, we have to have everything but the rate we're searching for. That's what we're searching for. So go down our problem. Do we have x? Yes, it's 6. Do we have dx dt? Yes, it's 1. We don't have y. What do you know about a right triangle? If this is 6 and this is 10, how could we find that? Pythagorean theorem again. So I know that 6 squared plus y squared has to equal 10 squared. If there's a missing thing that you don't have, there's got to be a way to find it. In this case, it's just a triangle. At that exact moment, the bottom is 6, the hypotenuse is 10. Find the other leg by using Pythagorean theorem. 36 from 100 is 64, so y is 8. So now we know x, dx, dt, and y, so we can find dy, dt. Let's shove the stuff into the problem. So this is 2 times 6 times 1 plus 2 times 8 times dy, dt equals 0. Now that's just a problem that needs solved, nothing crazy. So that's 12 plus 16 dy, dt equals 0. Move the 12 to the other side, it becomes a negative. Divide by 16. Now, why is that negative? I'll simplify it in a second, but this is positive because the distance from the wall is getting larger. This is negative because the distance down, that distance from the ground, is getting smaller. So that's why this rate going that way is positive, but this rate is negative. And we should expect that if it gets smaller, it should show us by having a negative rate. And so that would be negative 3/4 of a centimeter, or sorry, of a foot. I'm stuck in the last problem one, of a foot per second. So at the exact moment when we are 6 feet from the wall, we are going at a negative 3/4 of a foot per second. Okay. So that is a second one. Let's look at one that has a cone shape. And this is a common problem. It says a water tank has the shape of an inverted cone. So make yourself a cone with a base radius of 2, so that's 2, and a height of 4, they've shown that here. If the volume of the water is being pumped into the tank at a rate of 2 cubic meters per minute, so that rate is getting higher, so that is a volume. So the volume is being added, so that's a positive 2 cubic meters per minute. And all of these were also in meters, so that's good that all of our rates match up. And then it says, find the rate at which the water level is rising. So that would be our change in our height. So what is dH dt? When the water is 3 meters deep, so when the height is 3 meters. So I've just kind of pulled out what I know. Now, normally, if you asked me, what is the volume of a cone? The volume of a cone is 1/3 pi r squared h. Now, look at what variables we have over here. When we're searching for our equation, the variables that we have over here are h and v. We've got this extra one. We've got that r. We can't have r in the problem because we don't have any information about how the radius is changing. So we have to substitute something in. If you take a cross section of this, and I'm going to draw this little cross section down here. This is always true about a cone. A cone always creates what I call a nested similar triangle. So this is H, this is R. This entire thing is 4. This entire thing is 2. Back in geometry class, you should have learned that the sides of a similar triangle are proportionate. So if I go height to radius should equal 4 to 2. Now I need to solve for radius here because I need to take out the r that was in this problem that's causing an issue. I don't need three variables. I only need the two that are dealing with the rates I'm concerned about. So this R is screwing up the whole thing. But I can solve this for R very nicely. So if I cross multiply, I get that 2R, or I'm sorry, 2H is equal to 4R. So R is equal to half of H. So I know that the relationship between H and R is the radius is always half of the height. So I get to take this out and I get to replace it with 1/2 H. So let's do that. Now that looks disgusting the way that I see it. So let's make it prettier. If I square 1/2, I get 1/4. 1/4 times 1/3 is 1/12. Let's stick the pi on top of that because that's all kind of a constant that goes with it. So let's just stick the pi on top of the 12. And then I have an H squared times an H. I have an H cubed. Now, keeping that pi over 12 there as the number will make it so we just don't forget the rules, that it just hangs along for the ride. Now we're able to differentiate with respect to time. So we get dv dt equals pi over 12, hangs along for the ride. This is 3h squared dh dt. So now we're ready to go. Okay, now you got to check your work now. I'm searching. Let's highlight what we're searching for. We're searching for dh dt. Excuse me. We know dv dt is 2. Great. We know h is 3. Great. We're going to be able to solve for the thing we're looking for. So let's do that. Let's substitute the values that we know. dv dt is 2. H is 3. So technically, that is 27 pi over 12 dh dt. Now, 27 pi over 12, they're both divisible top and bottom by 3. Let's make that a little nicer. That would be 9 pi over 4 dh dt. So all we got to do is flip over that 9 pi over 4, flip it, and take it to the other side. So that would become 8 over 9 pi is our dh dt. And what are our units? That would be meters per minute. dh tells us it has to be the length stuff on top, meters. The dt on the bottom tells us we have to have time in the bottom. So that is meters per minute. So that is a related rate for a cone. That's a pretty common problem they like to do. So I don't think there's much here that you have to write, if anything. But let's just go over the rules one more time. As you read the problem, it's not a bad idea to pull out some of those rates. Draw a problem, or draw the diagram. Draw a picture. Introduce notation or your rates and your variables. Express the given information in the required rates in terms of derivatives. So that's that dr dt notation. Here's your equation that relates the stuff. Then you're going to differentiate using the chain rule because you're doing it with respect to time. And then you get to solve. Okay. So dreads, the strategy, you kind of do the same thing every time. Read the problem, maybe reread it a second time and pull out what's my picture, how can I draw it, what information do I know, how those things are related. So let's look at this one. Another common use of the Pythagorean theorem is the cars or things traveling close to each other, things traveling further away from each other. So let's look at a picture. So it says car A is traveling west at 50 miles per hour. See, this is car A, and they are traveling west. So we are thinking about, we are going this way. Okay, and let's actually put dx dt is 50 miles per hour. So we're going to label the distance we are from this intersection, point C. So we're heading, car A is heading west to the intersection. Car B is heading north to the intersection. And then dy dt is 60 miles per hour. But both of those distances, we're getting closer and closer to that intersection. So let's make them negative to imply that the distance is getting smaller. Okay, so make sure that you include that negative. I always want to forget that initially, but okay. So now it says, at what rate are the cars approaching each other? So think about the fact that the distance between these would keep getting smaller and smaller and smaller. So that distance between them is your hypotenuse. So we are going to label that a z. And so we want to know what rate are they approaching each other when car A is 0.3 miles from the intersection and car B is 0.4 miles to the intersection. So let's think about everything we just pulled out of that problem. Just by reading that problem, we found the rate of car A, the rate of car B, the distance from the intersection of car A and car B. We found out we wanted to know how is the distance between them changing. So you'll notice we have that picture. We've pulled out the rates. So we've done these two steps. Now we're ready for the equation. Well, it's a right triangle. We're relating the sides of the right triangle. Good old Pythagorean theorem is what we're going to use. They like to throw the Pythagorean out there for sure. It's a common use problem. Okay. So now that we have our equation, we are ready to differentiate with respect to time. Now, when we do that, we get 2x, tack on a dx dt. 2y, tack on a dy dt. Equals 2z, tack on a dz dt. Now the distance between them is getting smaller, so we should expect dz dt also to end up being a negative number. If it is not a negative, something is wrong, okay? Now let's think about what we know. We are trying to solve for dz dt. There should be enough information that we know every other piece to plop into the equation. I know x, 0.3. I know dx dt, negative 50. I know y, 0.4. I know dy dt, negative 60. Ooh, I don't know z. But if I have a triangle where this is 0.3 and this is 0.4, can't I find that pretty darn easily? If you do Pythagorean theorem, I know that that would be 0.5. Just do Pythagorean. But that's actually a 3, 4, 5 triangle. Okay, anyway, so now let's plop the junk into our equation. Now we're ready to actually solve. So 2 times 0.3 times negative 50 plus 2 times 0.4 times negative 60 equals 2 times 0.5 times dz dt. Now 0.5 times 2 is 1, so that gets us our dz dt pretty nicely right off the bat. Okay, but let's do the calculations for this other stuff. 2 times 0.3 is 0.6 times negative 50 is negative 30. 2 times 0.4 times negative 60 is negative 48. Negative 30 plus negative 48 is negative 78 miles per hour. So the distance between them is negative because the distance is getting smaller and smaller and smaller. And it is negative 78 miles per hour because they're both kind of, think about both of their distances kind of combine in a weird way in order for that to happen. So there's another dreads problem for you to contemplate. Now the next one that we're going to do has some trig in it. Doesn't that sound so nice? Okay, let's do a trig one. It says, a man walks along a straight path at a speed of 4 meters per second. So first, we are going to draw a little triangle, okay? He's going this direction at a speed of 4 feet per second. What's up?
Just find out what you can find out and call me
What am I supposed to find out?
about my hair.
I think it's Wednesday, but I'll find out.
Yeah, let me know so I'll wait here for 10 hours.
Okay, I'm trying to teach. I'll talk to you later. Okay, bye. Deep breath. Okay. She freaks me out when she calls me, you know. She has, you know, problems anyway. Old age lady, Alzheimer problems. Anyway, so our x would then imply that dx dt is 4 feet per second. And that distance is getting larger. So that's why we need to make it positive. Okay. Now a searchlight is located on the ground. It is 20 feet. Here's a little searchlight. It is 20 feet out. That is a fixed quantity that is never changing. So that's why anytime it's a fixed quantity that can't change, just slap the number in the problem. Don't give it a variable, okay? Because it's whatever dt is 0, so you don't need it, okay? This is where I want you to put a theta. That searchlight is rotating, kind of following the man, okay? And it says the searchlight is rotating when the man is 15 feet. So when x is 15 feet from the point on the path closest to the searchlight, which is this little point right here. Okay, he's 15 feet away. So let's think about everything we know. We want to find at what rate is the searchlight rotating. So we want d theta dt. That rotation, that angle is getting bigger because we're rotating from that initial point he was, and then we're following him. So we should expect a positive number, okay? Now, let's think about a relationship between an angle and the side of a right triangle. We're going to have to use one of our trig functions, okay? Now, which one of our trig functions uses opposite and adjacent? The tangent. So I know that the tangent of theta is always going to be x over 20. Now remember those rewrites we did? I would write this as the tangent of theta is 1/20th of x. Okay, so now let's think about what we know. We know dx dt. We know that we want d theta d. We know x. Let's do our derivative. Okay. So if you do the derivative of a tangent, you get secant squared. But theta is not time, so we have to tack on a d theta dt. The derivative of 1/20 over x is usually just 1 over 20, but we have to tack on a dx dt. Now, here's where we have to go back and look to ourselves and say, okay, do we have everything we need? Okay, so we don't have theta, but we do, kinda. We know that the tangent of theta is opposite, they told us was 15 at that exact moment we're looking at, over 20. Now, if you go into a calculator and you do the inverse tangent of 15 over 20, we're going to keep it in radians, guys. You do get a funky value. It's 0. Wait, let's see. Let me tell you what it is in radians. So if you do the inverse tangent of 15 divided by 20, you get 0.6435 radians. Okay. 0.6435 radians. 435, sorry. 0.6435 radians. Okay, so now we have everything we need to plop into our equation. We are going to put in our dx dt, which we know is 4. We're going to put in our theta, which is 0.6435 radians. And so we know that we're going to have to find the secant of 0.6435 radians, and then we'll square it. Dx dt was 4. 1 over 20 times 4 is 4 over 20, which is 1/5, just to save us a little bit of time. Okay, so the secant of that 0.6435 is 1.25. So if we square that, we get 1.5625. Let's change this to a decimal. That's 0.2. So 0.2 divided by 1.5625, d theta dt is changing at a rate of 0.128 radians per second. So you would definitely need to do a calculator. Technically, you do have all the sides of your triangle. If the one is 15 and the one is 20, hypotenuse is 25. So the cosine is adjacent over hypotenuse 20 over 25. So the secant would be 25 over 20 and 25 over 20 squared. You also get the 1.5625. So, I mean, you can use your triangle or you can use a calculator, doesn't matter. Okay, so that one's kind of disgusting. Now, your job is to do the problems from exercise 2.8, the odds 1 to 31. The hardest part is setting them up. Use the instruction manual to see if you set it up right before you actually jump into the differentiation part. So I would suggest, as you're starting to learn how to set up these problems, try to do steps D, R, and E. Draw, what are the rates, what's my equation? Don't do any math. Check your work in the instruction or the answer manual. Did I get those 3 parts right before you actually jump into anything else? Okay. We are doing a project. There is a project that's coming. It is worth 50 points. The instructions are here. The answers are given, but you have to show your work. Because there are 10 of you, I think I'll probably add 4 more problems so you each get your own unique problem, but I'll get back to you on that. For now, please work on your 3.8 problems because you got to get used to how these work because these are tough. Okay, so there you go.